So thermodynamics video number 4, and we're on enthalpy of hydration. We all know what hydration is, don't we? Adding water. So let's put this together. Sodium chloride is a solid salt, but I can dissolve it into water and make sodium and chloride aqueous ions just like that. That is the enthalpy of solution there of sodium chloride. Okay, that's just one. It's a new enthalpy change, enthalpy of solution. But I can break that down using a Hess cycle into two separate steps. First of all, I could take my solid sodium chloride and I could turn that into dissociated gaseous ions. There we go. We know what that is, of course. That's the enthalpy of lattice dissociation. Okay, great. It's a big positive number. That's our big endothermic change there from right down the right hand side of our Born-Haber cycle. And now we can look at the amount of energy released if we turn each of those dissociated ions into aqueous ions. Sorry, those gaseous ions into aqueous ions. So that's the hydration enthalpy there. So that will be the hydration enthalpy of sodium, and this will be the hydration enthalpy of chloride. Okay, and then we've got a Hess cycle there, nice and simple. The overall enthalpy of solution of sodium chloride would be the lattice dissociation enthalpy of sodium chloride, and the two it's the sneezing season. The two hydration enthalpies there. Right. Okay, let's put in some numbers. So, lattice dissociation enthalpy of sodium chloride is 786, big positive number. Hydration enthalpy of sodium minus 406. Hydration enthalpy of chloride minus 364. So if I put those together, I get 786, 406, 364, and you'll notice they almost cancel each other out. In fact, the the enthalpy of solution for sodium chloride is just endothermic. If you want to do a quick practical now and you've got a thermometer in the house, stick some salt in some water, give it a stir, you'll see the temperature goes down ever so slightly. Okay, so a couple of things. The numbers almost cancel each other out. Big positive number followed by big negative numbers brings you almost to zero. That means that our enthalpy of solution is going to sometimes be positive just, sometimes going to be negative just. And the relative differences between these numbers will determine how easily our solid substance dissolves. So we can play with that a little bit, and we can see why sometimes these numbers go up and sometimes they go down. The enthalpy of solution, sorry, the enthalpy of hydration is negative. Hydration is always negative exothermic. Why? Well, bond breaking reactions are endothermic, bond forming reactions are exothermic. What bonds are we forming? Well, if we're dissolving our iron in water, then the little water molecules will maybe not bond in the kind of traditional way, but and they look like this, little Mickey Mouses. They will form strong forces with the iron there, Of course, if I think about our water molecule, it's something like H2O like that. They would bond. They would orientate themselves that way around because the water is polarized towards the oxygen. The oxygen's more electronegative, so it attracts more electrons away from the H's, so that should be a plus. There we go. So we've got a negative end and a plus end, or a plus kind of side. So the water molecules will be orientated so the negative side of the water molecule is attracted towards the positive side of the sodium. And a sodium ion can roughly group about 6 water molecules around it. You might want to think what a chloride ion would be like. A couple of other questions to think about. How could we increase these numbers? Well, if we had smaller, more highly charged ions, then that would increase the enthalpy of hydration because it would increase the polarizing forces acting on the water molecule, it would increase the attraction of the water molecules to the ion. But of course it will also increase the lattice dissociation enthalpy. So smaller, more highly charged ions will change both of these, and it's quite hard to work out just on paper whether something will dissolve or not. Okay, that's all I have to say about that. Just one last thing. If we think about an endothermic reaction, in terms of energy, we're kind of going uphill. This is the progress of the reaction here. Here's our energy profile diagram. Here's our sodium chloride solid and our sodium chloride aqueous. It has to absorb energy from the surroundings in order to dissolve. We just sort of accept that happens. But why does it happen? Exothermic reactions are downhill as far as the universe is concerned, but endothermic reactions are uphill. They require energy to be put in. So the question might occur as why do they happen at all, really? And that brings us neatly on to the next topic, which is entropy.